Welcome to today's deep dive. This one is specifically tailored for you, our learner, because we are getting into some seriously cool infrastructure stuff today.
Yeah, we are. It's a really complex world, but super fascinating once you get into it.
Exactly. And okay, I want you to imagine this. You're an engineer at Spotify, like back in the early days.
Oh man, the Wild West.
Right. So you've got this massive, rapidly growing fleet of virtual machines, and you're using this homegrown orchestration system. I think they called it Helios.
Yeah, Helios.
Right. And when you want to spin up a new service, you submit your request, and then, well, you just wait.
You wait a long time.
Sometimes almost an hour just to get an operational host to run your code in production.
Yeah,
And I mean, in tech time, an hour is just an absolute eternity.
it's a massive bottleneck,
Yeah.
especially for a company that's structured around, hundreds of autonomous engineering squads.
Yeah.
When your architecture requires constant, rapid iteration just to test new features, infrastructure latency becomes the enemy of innovation. Your deployment pipeline essentially dictates your product velocity at that point.
Right. Because if it takes an hour to deploy, you're not doing it 10 times a day. What stood out in the engineering logs we went through is that they eventually made the leap and migrated to Kubernetes.
A huge undertaking, but yeah.
And
Yeah.
suddenly, that 1 hour wait dropped down to seconds or, maybe a few minutes. But the truly compelling data point from our sources today is the density improvement.
The efficiency gains there were wild.
Yeah. After moving thousands of microservices to Kubernetes, Spotify's CPU utilization improved by a massive 2 to 3 times across the board. Okay. Let's unpack this.
Sure.
Because getting a 2 to 3 times efficiency gain on CPU isn't just magic. How does an organization actually achieve that level of density without accidentally starving their applications of the resources they need to survive under load?
Well, it really comes down to incredibly precise boundary setting at the container level.
Mm.
You can't just flip a switch to scale your systems or pack them tighter.
Right. There's no make it faster button.
Exactly. You first have to define the physical realities of the containers running your code. You can't scale what you haven't properly measured, which brings us to the absolute foundation of Kubernetes scaling.
Requests and limits.
Yes, requests and limits.
So before we can multiply our pods to handle a tsunami of web traffic, we really have to look at how a single pod consumes resources. In the Kubernetes ecosystem, requests and limits serve very different mechanical purposes.
Very different, yeah.
A request is essentially the guaranteed minimum amount of a resource. Like, it's the baseline capacity the system reserves for your container to function.
Under the hood, that promise is enforced by the Kubernetes scheduler. So when a pod is submitted, the scheduler actively evaluates the requested CPU and memory against the available unallocated capacity on every single node in the cluster.
It's doing the math before it places the pod.
Exactly. If your pod requests, say, 400 megabytes of memory, and no single node has that specific chunk available, your pod just stays in a pending state.
It won't even try to run.
Right. It will not even start.
Yeah.
Which is good because it prevents it from being scheduled onto a node where it would immediately crash or degrade other workloads.
Right, it protects the system. Then on the flip side of that, we have limits. This is the hard maximum boundary. For an engineer, we know memory is non-compressible.
Yes, that's a crucial distinction.
So, to use a physical analogy here, memory is like a rigid cardboard box. You have exactly that much space. If you try to pack too much into it, the box tears open and bursts.
That's a great way to put it.
But CPU is like a stretchy silicone bag. It'll hold the extra stuff, but it stretches thin, and carrying it slows you down.
Yeah, that analogy perfectly captures what's happening. The underlying Linux kernel mechanics handle those two scenarios very differently. The limits are enforced by a Linux feature called COD groups.
Control groups, right?
Yeah, control groups. If your container hits its memory limit, if it overflows that rigid cardboard box you mentioned, the kernel really has no choice but to protect the rest of the system.
It has to step in.
It invokes the OOM killer, the out-of-memory killer, and your process is instantly terminated. The pod just fails.
Brutal. But with CPU being compressible, overflowing that stretchy silicone bag doesn't trigger a crash. The quick groups mechanism simply throttles the container.
It slows it way down.
Right. It artificially restricts the CPU cycles your application is allowed to consume over a given time slice. The application stays alive, but its performance degrades heavily.
Which is arguably the more dangerous scenario in a microservice architecture.
Oh, really? Why is that?
Because an RM kill generates a hard failure. It triggers immediate alerts, restarts, something went wrong. CPU throttling is insidious.
Ah, because the pod is technically still running.
Exactly. It's healthy according to basic uptime checks, but it's responding so slowly that it blows up your entire latency budget. Your downstream services start timing out, and your users experience a broken application without any critical failure alarms going off.
Oh, wow. That sounds like a nightmare to debug at 2 a.m.
It absolutely is.
The documentation points out that setting your limits too low to, artificially constrained costs actually causes more harm than good in those scenarios.
It does. It causes so many silent failures.
In fact, if an engineering team wants guaranteed quality of service, meaning the pod is never evicted unless the node itself is fundamentally compromised, they should set their requests exactly equal to their limits.
Yeah, doing so assigns that pod to the guaranteed QoS class. The scheduler knows precisely how much resource that pod will ever consume, meaning there's zero guesswork about node capacity.
No surprises.
Right. If you don't set these baselines correctly, if you misunderstand how crew groups handles the rigid box versus the stretchy bag, the automated scaling tools we rely on later in the pipeline are going to fail spectacularly.
Because they're basically operating on flawed foundational metrics.
Exactly.
Okay, so once those foundational boundaries are set accurately, we have to handle traffic surges. And that introduces the autoscalers. Our sources detail 3 main layers of scaling.
The three musketeers, essentially.
Yeah. First, the horizontal pod autoscaler, or HPA. This operates by stamping out more pod replicas to distribute the load. Then the vertical pod autoscaler, VPA, which adjusts the CPU and memory requests of your existing pods based on historical usage trends.
Making the pods themselves bigger or smaller.
Right. And finally, the infrastructure layer, like the cluster autoscaler or Carpenter, which provisions entirely new virtual machines when your physical servers are full.
But putting all three of those tools in the same cluster without strict architectural boundaries creates absolute chaos. The engineering blogs actually refer to the conflict between HPA and VPA as a death spiral.
A death spiral, that sounds dramatic. Let's trace the mechanics of that spiral. Imagine HPA and VPA are both monitoring the exact same metric, like CPU utilization.
Okay, setting the stage.
Traffic spikes, and the pod's CPU hits 80%. The HPA controller evaluates that metric and determines it needs more pods to spread the load, so it updates the replica count.
But at almost the exact same polling interval, the VPA controller reads that same 80% CPU utilization.
Oh.
Yeah. But VPA's logic dictates that the pods themselves are simply too small. To apply its new size recommendations, VPA uses a mutating admission webhook. It actually has to evict the running pods to recreate them with the newly enlarged CPU boundaries.
Wait, so now the cluster has more pods from the HPA and significantly larger pods from the VPA?
Exactly. Because the compute capacity just skyrocketed, the CPU utilization plummets down to, say, 20%.
And then HPA sees 20% and triggers a scale-down event, deleting replicas. VPA sees 20% and triggers another eviction wave to shrink the resource boundaries.
And then the CPU utilization spikes again because the cluster is suddenly starved of capacity and the loop repeats infinitely. Your application is effectively offline because the pods are constantly being terminated, resized, and recreated in a tug-of-war between two automated systems.
Okay, wait. If Kubernetes is designed to be this brilliant industry-standard orchestration platform, why does it allow its own native autoscalers to fight each other like that? Why isn't there a built-in collision detection system?
What's fascinating here is that Kubernetes fundamentally operates as a declarative framework of raw, unopinionated tools.
Unopinionated.
Yeah, it provides the mechanisms to observe state and react, but it relies entirely on human architecture to assign jurisdictions. The control plane doesn't know your business logic. It just executes the controllers you enable.
So the architectural fix is strict separation of duties. The standard practice is to never run HPA and VPA on the same metric for the same workload.
Never.
I read that many teams run VPA strictly in recommendation-only mode, where it analyzes usage and outputs data to a dashboard, but its mutation webhook is disabled, so it never actually touches the running pods.
That's a very common, very safe approach. Or, if an architecture requires both to be fully active, they are assigned completely different operational domains.
Like what?
Well, the HPA is configured to scale out based purely on CPU utilization, while the VPA is restricted to vertically scaling memory boundaries to prevent OM kills. Since they're evaluating entirely different resource metrics, their reconciliation loops never intersect.
Ah, that makes perfect sense. They stay in their own lanes. And while they handle the application layer, the node autoscaler handles the underlying servers. For teams running on AWS, Carpenter is rapidly replacing the traditional cluster autoscaler, right?
Yeah, Carpenter is huge right now. The traditional method relied on rigid node groups and auto-scaling groups, which meant waiting minutes for a generic server to boot up and join the cluster.
Minutes are too long.
Way too long. Carpenter abandons node groups entirely. It evaluates the exact resource requirements of the pending pods and directly calls the AWS EC2 Fleet API to provision a custom-sized instance in seconds.
In seconds, wow. Bypassing the autoscaling group abstraction is what gives Carpenter that speed.
Absolutely.
But having blisteringly fast node provisioning and perfectly isolated pod autoscalers doesn't matter if the metric triggering the entire chain is fundamentally flawed.
Oh man, this is where so many teams get burned.
Which brings us to a massive architectural trap. Relying purely on CPU utilization is incredibly dangerous for asynchronous or bursty workloads.
It really is.
Let's look at the celery worker example from our research. Celery processes background tasks. Say you have an external queue that suddenly jumps from 200 tasks to 6,000 tasks.
That is a massive demand surge.
Huge. But the CPU utilization of your worker pods might stay perfectly low, like hovering around 10 to 30%.
And it stays low because the workers are heavily bound by I/O operations, not compute. They spend most of their time waiting on network calls to a database or polling the broker for the next message.
They're just sitting there waiting.
Exactly. From the perspective of the Linux 3 groups, the processor is practically idle.
Here's where it gets really interesting. Scaling on CPU for a background queue is like a restaurant manager looking at the electricity bill for the ovens to decide if they need to hire more waiters, instead of just looking at the line of angry customers out the door.
I love that. That is the perfect illustration of why infrastructure metrics fail business flow problems.
Yeah.
The metric has absolutely nothing to do with the actual bottleneck.
Right. The HPA controller sees 20% CPU and refuses to scale while users are waiting forever for their jobs to process.
So the architectural solution here is semantic auto-scaling. You scale based on real-world demand and business logic rather than what the operating system kernel reports.
But Kubernetes is blind to my business logic out of the box, right? It only reads standard resource metrics like CPU and memory via the native metrics server. Are we writing custom scripts to force it to look at the celery queue?
Not scripts, exactly. We rely on a bridge component, typically Prometheus combined with the Prometheus adapter.
Okay, how does that work?
Prometheus is configured to scrape custom application endpoints. It pulls metrics like celery queue depth or raw requests per second directly from the application code. The Prometheus adapter then translates those custom metrics into the specific API format that the Kubernetes HPA controller inherently understands.
Ah, so the HPA controller stops looking at the CPU entirely and starts tracking the queue depth metric provided by the adapter.
Yes.
If the queue crosses a defined threshold, like, say, 500 pending tasks, it instantly stamps out more replicas, completely ignoring the fact that CPU utilization is only at 10%.
Exactly. And for event-driven architectures, the sources highlight an even more specialized tool called KEDA, the Kubernetes Event-Driven Autoscaling Framework.
KEDA. I've heard a lot about this lately.
It's a game changer because it acts as both a metric server and a controller. It natively understands dozens of external systems like an AWS SQSQ or a Kafka topic. It pulls those event sources directly.
And because KEDA is pulling the source itself, it doesn't even need a running application pod to report the metric.
That's the magic of it.
That means KEDA can scale your deployments all the way down to absolute zero when the queue is empty, saving massive amounts of compute budget, and then instantly spin up pods the moment a single message hits the broker.
It's incredible for cost savings. But configuring semantic autoscaling introduces a new challenge: determining the correct threshold.
Right. You can't just guess.
You really can't. You don't just arbitrarily decide that 500 tasks in a queue or 80% CPU is the magic number to trigger a scaling event.
The documentation stresses rigorous load testing to find those thresholds mathematically. Teams use tools like K8s or Locust to inject simulated traffic into a staging environment.
And the goal isn't just to see if the application survives. It's to map the exact point where latency degradation begins.
You're looking for the inflection point.
Exactly. If your load tests prove that API response times become unacceptable when pod CPU hits 80%, you cannot set your HPA target to 80%.
Why not?
Because scaling takes time. The control loop has to evaluate the metric, the scheduler has to find a node, and the container runtime has to pull the image and start the process.
Oh, I see. If you wait until you are at 80% to start that process, you're already failing your users.
Precisely. You have to build in a headroom buffer. If the breaking point is 80%, you might set the scaling target to 60%. That 20% gap is the safety net that gives the cluster enough time to provision new pods and absorb the traffic before the user experience degrades.
That makes total sense. Okay, so with those thresholds mapped, you have a highly intelligent, custom-scaled backend. The resource boundaries are locked, the autoscalers are strictly segregated, and the system is reacting to semantic business metrics.
A beautifully optimized backend.
But all of that backend optimization is useless if the traffic can't even get into the cluster. How do we prevent the entry point from becoming the new bottleneck?
The front door.
Right. The traffic has to pass through the API gateway. And according to the best practices from Solo.io and our sources, massive enterprise systems must move away from using a single monolithic gateway.
It's a single point of failure.
Yeah. The modern approach is a tiered gateway architecture, utilizing multiple Istio ingress gateways managed by control planes like GluEdge or GlueMesh.
Right. They stop funneling all inbound requests through a single entry point and start routing traffic by archetype.
What does that look like in practice?
Well, a standard implementation provisions one dedicated gateway purely for user interface traffic. A second, entirely separate gateway handles machine-to-machine API requests. And a third, highly isolated gateway is dedicated exclusively to transactional or payment traffic.
Okay, I have a practical question about this. If separating gateways for UI, API, and transactions is so brilliant, if it isolates faults and prevents system-wide crashes, why do so many teams default to using just one massive gateway to begin with? It seems like a glaring architectural oversight.
If we connect this to the bigger picture, it is really a byproduct of how engineering organizations evolve. When you're a startup, infrastructure simplicity is a survival mechanism.
True, you just need to ship.
Exactly. A single ingress gateway is easy to deploy, simple to monitor, and cost-effective. But as you transition to enterprise scale, the physics of network traffic change. You run into catastrophic, noisy neighbor issues.
Meaning one specific traffic pattern consumes the shared resources and starves out everything else.
Precisely. Consider a scenario where an attacker launches a massive DDoS attack against your public search API. Or perhaps a poorly optimized front-end script traps users in a loop, spamming the server with refresh requests.
I've definitely seen that happen.
Right. If all traffic shares a single ingress gateway, that flood of API or UI requests exhausts the underlying Envoy proxy's connection pools and memory limits.
And so the gateway gets overwhelmed just dropping the bad traffic, which means legitimate requests get dropped too. Your payment processing traffic, the actual revenue engine of the business, can't get through because a front-end glitch consumed the entire ingress pipeline.
Splitting the gateways eliminates that shared failure domain. It provides hardware-level traffic isolation. You also gain granular security perimeters.
Oh, like what?
Well, your transactional gateway can enforce mutual TLS and strict external authentication rules that would just add unnecessary latency to a public UI gateway. You don't need that heavy security on someone just browsing the homepage.
Furthermore, they scale independently. You can apply the HPA and pod disruption budgets directly to the specific gateway that needs it. The UI gateway might scale out to 50 pods during a marketing push, while the payment gateway sits quietly at 3 pods.
Exactly.
Yeah.
Though, to manage the complexity of routing rules across multiple gateways, the sources heavily emphasize using GitOps, specifically controllers like Argo CD.
Argo CD, that runs a constant reconciliation loop inside the cluster, right?
Yeah, it compares the live configuration of your gateways against the declarative YAML files stored in your Git repository. If an engineer manually tweaks a routing rule via the command line to fix a bug, Argo CD detects the configuration drift and immediately overwrites it with the approved Git state.
It just stomps on the manual change. I love that. It entirely eliminates manual configuration drift in production environments.
It forces discipline.
There was also a very specific operational rule in the GluEdge documentation about auto-scaling these gateways. It states you should actively auto-scale the data plane, meaning the Envoy proxies doing the actual packet switching, and you should scale the XDOS services handling the security validations. But you should never scale the control plane.
Never.
Why would scaling the central management piece be a bad idea?
Because it demonstrates a fundamental misunderstanding of how a service mesh operates. The control plane doesn't process user traffic. Its only job is to calculate routing tables and push those configuration updates down to the Envoy proxies.
So adding more control plane pods doesn't add any bandwidth or throughput capacity for web traffic?
None at all. It just burns compute resources and potentially introduces state synchronization issues between the control plane replicas.
Oh, because they're trying to sync with each other unnecessarily?
Yeah. The Envoy proxies in the data plane are the workers carrying the boxes. The control plane is just the manager holding the clipboard. When the warehouse gets busy, you hire more workers. You don't hire 10 more managers to hold the same clipboard.
That is a brilliant way to put it. So what does this all mean? We have gone on quite a technical journey today.
We really have covered a lot of ground.
We started by examining Spotify's massive efficiency wins, which revealed that true density requires understanding the rigid cardboard box of memory and the stretchy silicone bag of CPU throttling. We detangled our autoscalers, ensuring HPA and VPA operate in separate jurisdictions so they don't tear our pods apart in a death spiral.
And we also move past the limitations of infrastructure metrics, using tools like the Prometheus adapter and Kita to scale dynamically based on semantic business cues, mapping our thresholds with precise load testing.
Right. And finally, we engineered a fault-tolerant front door, splitting our monolithic ingress into a tiered gateway architecture so a simple UI glitch can never exhaust the connection pools of our payment processing systems.
For you listening, applying these architectural principles is the dividing line between reactive and proactive engineering. It is the literal difference between waking up to a 3 a.m. PagerDuty nightmare because a shared gateway collapsed under a burst of traffic, and waking up to discover your distributed systems quietly and autonomously scaled to handle a massive viral event while you were sound asleep.
It is the difference between hoping the system survives the load and mathematically engineering it to thrive under pressure.
This raises an important question about the trajectory of our industry. We discuss Carpenter directly provisioning bare metal and EC2 resources in seconds. We explored event-driven frameworks like K8s, scaling massive applications to absolute zero when the queue is empty. We are rapidly approaching an era of truly invisible infrastructure.
Invisible infrastructure that completely shifts the role of the platform engineer.
It does. Think about it. If the control plane can perfectly and autonomously predict demand, provision the hardware, and adapt to its own size in real time based on business logic, does the traditional concept of human capacity planning even exist in 5 years?
Wow.
Or will engineers simply become budget managers, setting upper financial limits while the autonomous systems handle the entire physical architecture?
Wow.
We've come a very long way from waiting an hour for a single server to boot up.
We absolutely have. And that shifting paradigm is an incredible thought to leave on. Keep questioning the default configurations, keep exploring the architectural metrics that actually matter, and we will see you on the next deep dive.